Hey guys, I just wanted to give you a video on Richard Parker's famous Egyptian calendar. This is from his book called Calendars of Ancient Egypt, and Richard Parker did this. And it seems like all the I guess Egyptian scholars or whatever they like to refer back to Parker, and he did an amazing work. But he has some errors in it, I think, and this is the main table from his book, and it's based on the Carlsberg papyrus, and I guess there's number 9 papyrus. And in the Egyptian calendars, there's 3 parts. This is supposed to be pronounced Octan, something like that, PRT and SMW. Anyways, each of the 3 parts of a calendar year have 4 months, and 365 days, and it's supposed to be 365 days repeating. There's no leap day or leap year, and so it just repeats every 25 years. So year 1, year 25, and so basically there's numbers for 6 of the 12 months, and so what there is 12 months, each 30 days long, and then 5 extra days at the end of the year called epigemenon or something like that, epigemenal. Anyways, so this is the start of year 1. Lunar day 1 falls on month 1. I'm sorry. The month 2 of the first period, day 1, that's when the lunar day occurs, in the start of the cycle. I kind of think what happens is that when the next 25 year starts, they look for this day right there, and if it's not a lunar day, lunar moon right there on that first day, then they shift the calendar over a little bit. So what he does, Richard Parker does, is he goes through. Most of his book is like looking at the actual years of like the when the moon conjuncts with the Earth, and if you're in like Egypt, Thebes, Egypt, or whatever, and you're looking in the morning while it's still dark out before it turns light, will you be able to see the moon? And this is like, no, you can't see it on August 16th, according to Parker. So anyways, he says the first morning you can't see it. In other words, there's the waxing moon and waning moon. So when the moon's getting smaller and smaller, it's called waning. And on August 16th, that's the first morning that you can't see the moon on this date here. And then the evening, a couple days later, the first time you see the first sliver of the crescent moon, that's August 17th. Problem is, he wrote his book in like 1950, and so basically they didn't have computer programs back then, so everything was done by mathematical tables, and I think there's some errors. Okay, so he goes through the books, and this is for the year 144 AD, and the reason he starts here has to do with, that's the year that they think the Carlsberg number 9 papyrus was written, and so he looks at this year to start with, and the 25-year cycle that this is in starts 25 years previous, well, actually, it would be 25 minus this date here. Okay, so he looks at also other years, and like 856 is where how far back he goes. Okay, and he claims that every 500 years there would be about a 1-day shift in the schedule. In other words, they would be off about 1 day, and I think he's right on that. So basically, if we go from back 1,000 years, 144 back to 856. That's 1,000 years. So they should be off about 2 days. Okay, and I agree. He also wants to fill in the data. So he looks at 357, 356, 355, whatever. Looks at all these other dates. And then he looks at historical data where you have some other type of Egyptian writing hieroglyphs on walls or clay cuneiform tablets or papyri or whatever. And he looks at other data that actually gives dates. You know, this is the Egyptian stuff. And this is its translation, what he thinks it is. And the month of the year, and this is the Julian month. So he goes through all these books and gets all this data. And so what I did was I put it in an Excel spreadsheet. I don't know if anyone else has done that. I'm sure people have, but I don't know of any data. So basically what I did was I put it in an Excel spreadsheet, and I can use filters and stuff like that. If I take all the filters off and shoot. Oh, there's another filter. So here's all the data, and I just go back in time. This is the Julian month, Julian day, Julian year. This is it's all written out. And then you have the Egyptian month, the day of the month, and the Egyptian year, the 25-year cycle. And then, of course, this is where it counts up to 365 days. Okay? And I just scroll through it. So, for example, if we go back up here to first day of the Egyptian year is right there. Starts out 1, 2, 3, and goes to 365. The previous year goes to 365. I kind of think there's some days that this changes, some years that this changes, that it might only be 364 days, and there's some Egyptian papyruses that say so, that make a case, not totally 100% positive, but kind of allude that this is the last day of the year on some days. This is the 13th month, what I call it. It's the epagomenal, I don't know how to say it, epagomenal days. And then this is the first month of the first period. Starts out day 1, goes to day 30. Okay, so that's Egyptian calendar. I took the data, and what I did was I just took the data from Parker, which is highlighted in green, and then I put in data from the SkyViewCafe, which is an online planetarium, modern day computer program. So what Richard Parker does is he looks at the morning invisibility moon and the evening visibility moon. So what I did was I looked at the SkyViewCafe, morning invisibility and evening visibility. And the way I did that with the SkyViewCafe, for example, I brought it up here, and you can select Thebes, Egypt, and it gives you the longitude and latitude and longitude, sorry. And you can look at the moon, and to look at the morning visibility, see it's all dark here, and you can scroll up, see, and that's when it's still light out, and it's behind this green background here. That means moon is below the horizon. So if we scroll forward in time to when it comes above the horizon, it's already light. So it's like when the daytime you can't see the moon. Here that shows you the moon. You can see the light background here. That's like means it's daytime. So basically, you can scroll back in time. Go back one more day, and now you notice that you can see a sliver of the moon, but it's still kind of light outside. So they wouldn't be able to see that. So you go back a little bit more and see the skies get darker and darker. Okay, so you can see now it's dark outside. It's still the morning, 5:35 in the morning, and it's the 13th of the month. So we go forward one day. Now it's behind the Earth, so that would be the first invisible day on the 14th. And you can do the same thing for the evening. So on the 16th, January 16th, you can see the first crescent. Go back one day, it disappears. So you can. This is how I determine using SkyViewCafe whether it's morning invisibility or evening visibility, and I put that in tables in the Excel spreadsheet, and then I put all the data here: SkyViewCafe morning invisibility, evening visibility, Parker's morning invisibility, Parker's evening visibility, and I came up with this nice chart. And basically, there's data points all over the place, and in some years I did several months, and I put the data out on here, and so you'll see 3 lines in a row, 3 dots in a row, and what scientists use is what they call best line fit of the data. In the real world, a lot of times the data isn't a perfect line. And in reality, the moon has an ellipse around the Earth, and it's not a perfect ellipse. There's other gravitational forces on it, and so anyway, the best line fit was not something that I generated with a formula. It was just Excel. This is Excel. It generated this chart. You're right. I'm not going to show you how to do it, but it generated this fit. And so you have 4 lines, best line fits, and they represent the evening visibility for SkyView, evening visibility for Parker, morning visibility, invisibility Parker, morning invisibility SkyViewCafe. And what each one of these horizontal lines is a day. So this 0 here, I can't see it. This is lunar day 1, lunar day -1, lunar day -2, etc. And you'll notice that the orange line, the difference between the orange line and the yellow line is about a half a day. So what this says is that Parker averages a half a day error compared to the SkyViewCafe for the evening visibility. Same thing down here for the morning invisibility. Parker averages about a day error from the morning cafe. So I really think that the best SkyViewCafe really is the best. It's better because it's more modern. It's a computer program than Parker. Anyways, you look here. This is lunar day 1, and this is where data crosses the curve. If you look at the 4 best fit lines, these 2 come the closest to hitting lunar day 1, and at this point in the axis, in the time axis, and this time right here is, you can see there's 100. So this is about 100. This is the 144 AD point here, where the Carlsbad 9 papyrus. Oh, that's misspelling. That should be U. Anyways, when it was written. So I feel like the graph closest to lunar day 1 here is Parker's, but he has an error, and that SkyViewCafe is right there, and so the best fit says that Skyview Planetarium evening visibility is what the Egyptians were using when the Carlsbad 9 papyrus, boy that's spelled wrong, was written. Anyways, the other possibility, and Parker likes to do this in his book, he says if you go back in time, he says, when did the thing originate? And so if you go back to where lunar day 1 here, so if they started, where this SkyViewCafe online planetarium crosses Lunar Day 1, it's at around 700 BCE, right in there. So if Parker's right, Parker thinks it's morning invisibility, and that it started back here and it went down the line. That means this is saying when it started was right there. In Parker's viewpoint, it crosses right around there, which would have been about 275 BC, roughly. So, I guess that's about it. And I just wanted to show that video. It shows it much